As we move into doing more project-based work in the class, it's important to broach the concept of geodatabase design. This is working to find the best representation in your computer of the real-world geography that you're trying to build a GIS around. Geography's complicated. We have many different layers that we need to create to represent the real world around us. These layers can be related to each other. They can be made up of points, lines, and polygons. They can have additional, more complex structures built on top of these points, lines, and polygons, like utility networks or transportation networks, topologies, surfaces, and other information. This representation shows the layers used to represent the real world and the attributes that are part of those layers. In ArcGIS, we can represent geography in a number of ways. The simplest ways are the points, lines, and polygons that we've been seeing this semester. As mentioned, you can also have additional constructs on top of these simple feature types like networks and topologies. We can also represent geography through continuous surfaces, raster-based data, and things like locations that can be represented by addresses or a set of coordinates. These geodatabase elements should be familiar to you at this point. We can have non-spatial tables in our geodatabases. We can have feature classes of points, lines, and polygons, as well as additional annotations, dimensions, and routes. These may be organized in feature datasets. We can also have things like geometric networks, network datasets, terrains, topologies, survey datasets, and a whole host of other things. These geodatabase elements can have behaviors defined by attribute domains and topology rules, to mention a couple. So the purpose of geodatabase design and the goals of geodatabase design are important to understand. In order for GIS to be effectively implemented, you really need a good database design to start. Asking the appropriate questions is key to building a database that will support your organization, your needs, and your goals. Questions like who will be using the database and how they'll be using it, if it will be shared, the different people or departments responsible for maintaining the database or parts of the database, and what kind of business processes will the database support. The design process is where these goals are defined. You look at design alternatives and make sure that you have options if your design doesn't support your needs. And you agree on an implementation plan to implement your database design. Essentially, you're deciding where you are, where you're going, and how you're going to get from one place to the other. So a functional and well-organized database does the following. It satisfies objectives and supports organizational requirements. It contains all the data of the organization, but does not have redundant data. It organizes data so that different users can access the same data. It may accommodate different views of the data, like streams may be line features at a small scale showing a large area, but if you zoom in to the city of Asheville, the river, French Broad River, may become a polygon feature class. Distinguish applications that maintain data from those that use it. You may have a web server, an internet map site, publishing the data and providing some kind of application to use the data for an end user, whereas you use ArcGIS Desktop to edit and maintain the data. You can appropriately represent codes, appropriate representations, codes, and organizing geographic features is another objective of your design. So design takes time. It is very important to spend the time up front. It's a pay me now or pay me later kind of thing. If you don't spend the time up front to design your database, once you build it, it may not support your business needs. So you'll have to go back to the drawing board and redesign, and you'll spend more time and money doing that. If you don't design them, your database may not meet the requirements to support things like mapping and editing and analysis. You might have duplicate data or missing data, and there may be a lack of necessary management and maintenance techniques to keep the database up to date and usable. So here are some guidelines to think about. It's an iterative process. You need to get a bunch of stakeholders or users involved in the process. You take it one step at a time. You get all the users in a meeting or multiple meetings. You come up with what they think they need in the database, and you start to build it, and then you come back to them and ask them if what you've done is what they were thinking. So it's an iterative process. You want to be creative and create deliverables. Make sure your organizational goals and objectives are in focus. You don't want to start adding data too prematurely. You want to make sure that the structure, or what we refer to as the database schema, is built and ready for the data before you start adding it to it. Make sure to document what you do. Be flexible, plan from your model, and pilot your design. Piloting your design in a small area will allow you to go back to the users and again continue with that iterative process to make sure the database supports the organization's needs. And this represents the database schema. So again, the database schema is the structure or design of your database, not the contents of your database. So in this case, you're looking at a database design generated from a unified modeling language tool like Visio. Visio and other UML tools are tools that allow you to design and model a system, and you can design and model databases with them very effectively. So this shows all of the feature classes, their relationships with each other, the attribute fields that are stored with each feature class. This is the state boundaries feature class. You can see it is a line feature class, geometry polyline. It has a set of fields. For each one of those fields, there is a type of data that can be stored in the fields. Some of them have domains and other information. So you can see this document very details every feature class, all of their attributes, attribute types, spatial references, domains, subtypes, topologies, all that kind of information. Here's the domain here. So this is the schema of the database. You want to determine all of this information before you start adding data. Make sure you know at least the feature classes that will be in your database, or the layers, the feature class's geometry, whether it's going to be a point, line, or polygon, what attributes each feature class will have, and domains that will be part of the attributes, and how these feature classes relate to other feature classes, and if they'll be used to build an additional construct like a network or a topology in addition to the simple feature classes. Also think about how you'll organize your feature classes into feature data sets. Esri has a lot of industry-specific data model templates. They're a great starting point to for your database design. You can see them there, and I've got an example on the next page. If you went to work for a sewer district and they said, design me a new database, the best thing for you to do would be to start with an existing database that was already designed. This is the database schema in a UML model from the ArcGIS Sewer Stormwater Data Model. You can download the structure, the schema, the shell of the geodatabase right from Esri and start importing your data into it. That's not really the best practice with these kind of data models. They are built to support many different sewer and stormwater organizations across the country. So an individual one there's far too much data in most of these data models, but they're a good starting point. So here are the design phases. These are kind of big, broad design phases. There's the conceptual model. That's when you're just talking with stakeholders and identifying the different kind of layers and tables and attributes and things that will be done with the database. The logical model is when you map your layers that you discussed to actual geodatabase elements, things like a point feature class or a geometric network. Once you map out everything you discussed with your stakeholders in your logical model, you can create the physical model, actually build the schema. So just a little graphic that shows these steps from your conceptual model, where you're just talking about the layers and the attributes and the tables, to mapping them to geodatabase elements like feature classes and topologies and networks, and then you're building the schema in the physical model. This came out of a geodatabase design book that outlines the steps of building a geodatabase, and from these 5 steps as a part of the conceptual design and the logical design. The conceptual design is modeling the user's view and defining entities and relationships, as well as identifying representations of entities, points, lines, or polygons. The logical design, matching to geodatabase models and different elements that are available to you in the geodatabase, as well as organizing into different geographic data sets. The more recent Esri documentation lists these 11 steps to geodatabase design, and they're a little bit more detailed, and I think they're a good reference to go by. You can see these using the link in Moodle. This is available on the ArcGIS desktop resources page, and this shows you these design steps. So we'll talk about each one, but I'd like for you to read about these as part of your required reading this week. So the first step is to identify the information products that you will create and manage with your GIS. Your GIS database design should reflect the work of your organization. So make sure to consider what your organization does, their current workflows and processes, and identify how these workflows and processes will be part of your new database and make sure that they're supported. Step 2 is to identify the key data themes based on your information requirements. So here you define more completely some of the key aspects of each data theme, determining how each data set will be used, if it's for editing or analysis, routing, specify where the map data uh, comes from, what maps will be made, all this kind of information. From there, step 3, you have to think about the scale ranges and spatial representations of each data theme at each scale. So, are you going to model cities as points, or are you going to model cities as polygons? So, as scale changes, the representation of our data often changes as well. So, make sure you understand how you're going to model each feature class and if this representation will change based on scale. You may have things represented at different scales in different ways. Also think about raster data and how you're going to represent raster data, whether it will be in a mosaic data set, whether you're going to build pyramids, how you're going to handle your different data at different scales. Step 4 is decomposing each representation into one or more geographic data sets. So these discrete features can be modeled as feature classes of points, lines, and polygons. You need to consider if you're going to have advanced data types like topologies and networks and terrains, and decide how things are going to be modeled in featured data sets, how you're going to model your raster data, and really start to build this into the actual constructs available to you in the Geodatabase data model. Step 5 is to define the tabular database structure and the behavior for descriptive attributes. So this is when you come up with all of the attributes that will be stored with your layers. An example would be if I wanted to create a point of interest layer for the national forest. What kind of attributes am I going to store for these points of interest? How about the name of the point of interest, the type of the point of interest, maybe a description of the point of interest? So that's starting to define the attribute fields, but you also need to define all of the possible values for those attributes. For instance, the type field. What kind of types of points of interest are there in a national forest? So for the type attribute field, I'm going to store text, and the types of points of interest might be a fishing location, or a picnic area, or a campsite, or a ranger station. All of these could be put into a domain or drop-down list for points of interest. But the point is, not only do you need to think about what attribute field you're going to store, but also the values that you're going to store for that attribute. From there, you define the spatial behavior, spatial relationships, and integrity rules. Number 6. For features, you can add spatial behavior and capabilities, and also characterize spatial relationships inherent in your related features for purposes such as using topologies and networks. So you want to think about any kind of topology rules or networks that you want to build, any advanced functionality. From there, you propose your geodatabase design. So you come up with a set of geodatabase elements you want in your design for each data theme. You look at patterns and best practices from other database designs like the Esri data models. Step 8 is designing and editing workflows and map display properties. You want to think about the editing procedures and integrity rules and make sure that you've got a set of processes in place for the person editing and maintaining the data, as well as how you're going to map it and how it will be used for mapping and analysis. You want to then assign responsibilities for building and maintaining each layer, who's going to build, populate, maintain the database, build a working prototype, review and refine your design, and then of course document your geodatabase design. Documenting your geodatabase design is very important, and there's many ways to do it. This is called a database design document, and it is the most accessible to people. It's easy to use. It's essentially a Word document where you have the feature class name, you have a description, and then a table that shows attributes, attribute types, and domains. It also lists the subtypes with this particular layer, relationships, topologies. So it puts everything in one document related to a layer. There's also classic layer diagrams, and they organize data into logical units. They focus on common data elements to help us determine things like attributes, associations, and spatial relationships. You can see this part of this diagram is referring to a topology feature class, and it has all of these layers that participate in it. It shows the ranks and the rules. You can also use unified modeling languages like Visio. These are good for large designs. Some database elements, geodatabase elements, may not be supported. These are used for database design in all kinds of industries outside of the GIS world. This is an example of one. To use something like this, you do need a unified modeling language program like Microsoft Visio. There is the Geodatabase Diagrammer that uses Visio to create, edit, and analyze geodatabase schema. You can learn more about it here, but know that it's really best for large designs, and you do need Visio to do it, to use it. So from there, how do you construct the database? You can create schema with some different wizards in ARC Catalog. If you have a database structure, someone could export it to XML, and then you could import it using ARC Catalog. From there, you import data, or you can import data. Importing data creates structure similar to that of those imported. You can use schema tools and also the ArcGIS diagrammer. So there's some different ways that you can do this. We oftentimes just use the ARC catalog wizards of right-clicking new feature class and defining the attribute fields and the types as you go. This is kind of the manual way here. Importing data builds schema as it comes in, case tools, or copying schema.